This question is a fun one about scuba diving. And the world record holder, Ahmed Gabir, in 2014, has gone 332 meters, or over 1,000 feet down in scuba diving. And we're told that the water pressure increases at a rate of 1 atmosphere for every 10 meters. Given that the pressure is already 1 atmosphere at sea level, what's the pressure experience in this depth? So if we have, sea level here, we already have 1 atmosphere. This is the sea level of the waves, and we can see, all right, there's 332.35 meters. All right, so if we want to know how many atmospheres this is going to be, we're going to take 332.35 meters and multiply it by 1 atmosphere per 10.0 meters. Meters will cancel, and that'll tell us how many additional atmospheres there are. And we get 33.235 atmospheres. But there's already one there, so 33.325 atmospheres. So that means the new pressure will be 34.325 atmospheres is what's felt. All right. What is the pressure in atmospheres? Well, we've got our atmospheres, atmospheric pressure. This 1 atmosphere that we're going to use, we go to our data booklet. What sense can we make of that? Is the old STP, which is what we're using, is 1.0 atmospheres. It's the definition, so that has an unlimited number of significant digits. We've got 10.0 meters, and since we're doing that there, that means we're relegated to 3 digits. So we would say the pressure in atmospheres would be 34.3 atmospheres. That's the pressure in atmospheres. What about in inches? Well, we can look for our conversion. Let's go with atmospheres to inches. 1 atmosphere is... It's actually not given to us on this chart, on this table. So we'll just skip over that one and not do inches. We'll do bars. And so 1 atmosphere is 1.01325 bars times 1.01325 bars per atmosphere. So we'll take that answer and multiply it by 1.01325. And we're going to get 34.6886135 bars. And we can report 3 digits again. So it's going to be, the pressure is 34.6 bars. And if you know, since we're multiplying by almost 1, the answer will be almost the same size, but a little bit larger. So we've got bars. Now we want kilopascals. The kilopascals is 101.325. So we're going to take this same number here and multiply by 101.325 kilopascals per atmosphere. Is going to give us 3,468.861375 kilopascals. You can see we could move that over and become megapascals, but we're asked to express it in kilopascals. 3 digits. So we're actually going to say, this is kind of weird because we can only write 3 digits for this. We're going to put 3.47 times 10 to the 3rd kilopascals. That's how many kilopascals it would be. Since we can only write 3 digits, we can't write 3,470. It's confusing. And since we only report those digits, we put it in scientific notation. And it would be better if we actually expressed it as megapascals. But it's asked for kilopascals. And millimeters. So let's go to the millimeters. Millimeters, 760.000. So we'll take this number again and multiply it by 760.000 millimeters per atmosphere. It's going to equal 26,018.6 millimeters. Again, we can only express 3 digits, so we're going to say 2.60 times 10 to the 4th millimeters. But really, this should be, we can combine the units if we're going to do that. So that if we're going to actually express it in millimeters, what we should do is write it that way. So 2.60 times 10 to the 4th millimeters. And again, we don't like to usually combine scientific notation, powers of 10 and metric prefixes. We usually like to combine them. So that's 10 to the 3rd, 10 to the 1, and so this becomes, milli becomes 0. So that becomes a 0. Milli is 1, just 10 to the minus 3rd times 10 to the 3rd is 10 to the 0, which is 1. So 2.60 times 10 to the 1 is 26.0 meters of mercury. And so that's just the fun we had in converting these units. All right, so we see here that when you're diving at depth, the lungs are like a balloon in terms of their expansion and compression. So if they're down way down below the surface of the earth, like down like this, you know, so here's someone's lungs, like this, they are going to be compressed incredibly. In fact, by 34 times the pressure that we experience on Earth. So that would be really compressing those lungs. But what happens is the scuba tank puts gas in to equal that, so our lungs stay the same size. So there's this huge 34 atmospheres of pressure on the inside pushing out to make sure our lungs don't compress. So how much longer would it be if this held his breath at the bottom? So the person takes in a deep breath way down here, and they hold their breath all the way to the surface, and as they rise to the surface, this pressure is going to stay the same inside, but it's going to decrease on the outside, so it's like blowing up a balloon. So we could use the gas laws for this and just say PV equals nRT. And all of this seems to imply a constant temperature. The gas constant's the gas constant, and the number of moles is going to be the same. It's a closed system. So the pressure times the volume is going to be constant. So if we take the pressure that's experienced, which should be expressed in kilopascals, and we know what that is 3.468861375 kilopascals times the volume, which is 5.700 times 10 to the 3rd milliliters, and milli is 10 to the minus 3rd, so we've got 5.700 liters. But we need to convert that to cubic meters, and our conversion for cubic meters is 10 to the minus 3rd cubic meters times meter cube liter. 1 liter is 10 to the minus 3rd cubic meters. So we're going to get 0.005700 cubic meters. So that's what we have at the baseline. So we've got 3.468861375 times 0.0057. And that constant is going to be 0.0197725. Now we repeat that calculation at the surface. So we've got pressure, volume equals this constant, 0.197725. The volume now, that's what we're looking for. So the volume is going to be 0.0197725 divided by the pressure. And the pressure at the surface is 1 atmosphere. And 1 atmosphere in kilopascals is 101.325. So we divide by 101.325.